How's it going, ladies and gentlemen? Mr. Donnie here again. This time we're taking a look at some practice problems for 19.5 Gibbs free energy. So objectives being to explain the significance of Gibbs free energy and what values are associated with spontaneous reactions, non-spontaneous reactions, and reactions at equilibrium, as well as calculate the change in Gibbs free energy using known values at standard conditions. So as far as the math goes, we're looking at this equation, which should look really familiar. The change in Gibbs free energy is equal to the sum of the Gibbs free energy of the products minus the sum of the Gibbs free energy of the reactants. All right. So number one, which of the following options is a standard Gibbs free energy of 0? There may be multiple or none. So Gibbs free energy of 0 means it's at standard temperature and pressure, and whatever phase or state of matter it should be in at that standard temperature and pressure. So H2O being a liquid doesn't work out because it's a compound. So we're looking for elements. If it's a compound, it can't be 0. You've made it somehow. So the standard is, we say standard Gibbs free energy is based on at an element at STP being in whatever phase you should expect it to be in. So it's definitely not A. Magnesium, solid. It is a solid at STP, so magnesium's looking pretty good. And then bromine being a solid. Actually bromine should not be a solid. It should be a liquid at standard temperature and pressure. All right, number 2. What is the value of delta G naught for the oxidation of solid elemental sulfur to gaseous sulfur trioxide? And then they give you the equation and they give you the values. So again, you go, let me look at what the values would be for the reactants and the products and see what the difference is. So I got 2 sulfur rhombic, so it's 2 times 32.1 kilojoules per mole, which is from the value, but I'm gonna have naked numbers because I don't feel like writing it out. Plus 3 times whatever oxygen's is. Hey, wait a minute, I don't see oxygen here. Why is that? Well, oxygen in its standard state at STP has a value of 0. So I'm just gonna not even write that. And then we got 2 SO3s. So 2 times whatever SO3 gas would be, negative 371.06. So when I do the math, I see that I start at a positive 64.2 and I end up at a negative 742.12. So what is the difference there? Well, I could do the products minus the reactants, and I end up with a negative 806.32 kilojoules per mole. Again, I always check to make sure that this number makes sense. I started at a positive value and I ended up at a negative value, so I should expect the sign to be negative, which is what I got. I'm always afraid I'm going to mess that up, so we always check it. Number 3, what is the value for the delta G naught in kilojoules per mole for the decomposition of gaseous sulfur trioxide to its components elements? So we have a pretty similar problem. Hey, wait a minute. This looks like the exact same thing, but flipped. Right, I start with 2 sulfur solid rhombic and 3 O2 gas, giving me 2 SO3, and then this one is the exact opposite. Well, guess what? Then you have the same value, 806.32, but the sign is different, positive kilojoules per mole. Right, so if you solved the one direction on number 2 here, going this way, it's negative. The opposite direction is going to be the same number, but flip the sign. All right. Number 4, given the following chemical equation of thermodynamic values for the unbalanced reaction at 1 atmospheres and 25 sal. These jerks like it's not me. These jerks gave you an unbalanced chemical equation. So first things first, you got to balance it. So I got carbon, hydrogens, and oxygens. Carbon, hydrogens, and oxygens. How many on the left side? Well, there's 2, 6 hydrogen and 2 oxygens. I got 1 carbon, I got 2 hydrogens, and I have 3 oxygens. Oxygens are going to be obnoxious. I'm going to save them for last. I'm going to put a 2 in front of the CO2 to fix my carbons. So now I got 2 carbons, but now I also have a total of 5 oxygens. I have 6 hydrogens on the left, only 2 on the right. So I'm going to put a 3 in front of the H2 there, which is going to fix my hydrogens, and they're going to be balanced. But now I also have a total of 7 oxygen atoms. Now what stinks is I can't get to 7 by counting by 2s. But what I could do is a little trick. So I go, hey, I need 7 halves of this. All right, so that's going to give me a total of 7 oxygen atoms. But the problem is I can't have a fraction. The 7 halves has got to go, right? So how do I fix that? Well, I times everything by 2. Now I have 2 C2H6s. If I do 2 times 7 halves, I just end up with 7. I do 2 times CO2, I got a 2 there, and 2 times, oh, I erased the 3. The 3H2O that was there is now a 6. So my balanced chemical equation, which I need to start, is going to be 2 C2H6 gases plus 7 O2 gases, arrow, 2 CO2 gases, and 6 H2O liquid. All right. Ooh, all right. So now I got it balanced, and oh man, what are they doing to me? I got delta HF naught and I got S naught, but I need delta G, so I'm gonna need some other equation here. The other equation is gonna be delta G equals delta H minus T delta S. So I need to figure out first what is my change in enthalpy, then I need to figure out what is my change in entropy, and then I can calculate my delta G. Jeez Louise. All right, so let me work on my delta H first. Delta H values. I got 2 C2H6s, which has a delta H value of negative 84.7, plus 7 O2s, which, hey, look at that, it's 0. So that works out, I don't have to worry about that. And then arrow, 2 CO2 gases, so it's 2 times negative 393.5 plus 6 H2Os, so 6 times the value for H2O, which is negative 285.8. These are all kilojoules per mole. So when I do this math, oh snap, I'm sorry, I erased too much stuff. This CO2 is really a 4, right? Because I had a 2 CO2 there and then I times it by 2, so that's a 4. I'm sorry that I'm just catching this now. There you go. Better now than never. So when I do this math, I get a delta H of, where did I write it? Negative 3119.4 kilojoules per mole. And it's you got to be careful. This is kilojoules, but then the entropy is going to be in joules. So this is like a multi-step problem. So let me figure out my delta S. Same kind of process. I got 2 C2H6s. So I look at that. I got 229.5 plus 7 oxygens, which has a value of 205. And then arrow, I have 4 CO2s, each has a value of 213.6. And 6 H2Os, each with a value of 69.9. So when I do my delta and I do the math, I end up with a delta S of negative 620.2 joules per mole Kelvin. So it's important that I make sure I fix one of these. Since they want my answer in kilojoules per mole, I'm going to fix my delta S from joules to be kilojoules. So I got to divide it by 1,000. So it's negative 0.6202 kilojoules per mole Kelvin. So now I can go back to this equation. My delta G equals my delta H, so negative 3119.4 kilojoules per mole, minus T delta S. My T is 25 Celsius, so I got to add 273 to that to get 298 Kelvin, times negative 0.6202 kilojoules per mole Kelvin. The Kelvin will cancel out, and when I plug and chug and get my final answer, I end up with negative 2935 kilojoules per mole. I think that's to the correct sig figs, but who knows? Maybe I didn't. So that should be your final answer. That was a bad one. That was rough. Number 5. The value for delta G naught at 25 Celsius for the following chemical reaction is what? So again, we go P4 gas has, oh hey look, delta G is 0. So I got 0 plus 6 times Cl2 gas. Oh, why'd they not put that there? Oh, because that is also 0. It's a pure element in the state you'd expect it to be at STP. Goes to 4 PCl3, which is right here. Oh, wait. Haha, they almost got me. Almost got me. That's a gas right there, right? So P4 solid is 0, but P4 gas is 24.4. Haha, trying to trip me up. So 4 times PCl3, negative 267.8 for each of those. So my reactants start at 24.4, and my products ends up at negative 1071.2. So I know my overall change should be negative. Start from positive and end at negative. So let me do the math. Products minus the reactants. And I end up with a number of negative 1095.6. And then the units are going to be kilojoules per mole. Yeah, that's number 5. Let's see, number 6, last, I don't know, second to last one for the section. For the following substances which have a standard Gibbs free energy of formation of 0, there may be multiple or none. So again, you're looking for an element at whatever phase it's supposed to be in at STP. So let's see, Si liquid. No, silicon should be a solid at STP, so not this one. Fluorine is a diatomic molecule, so it's definitely F2, and it's definitely a gas at that temperature, a standard temperature. So this one looks good. What about nickel? Nickel, is it a solid at standard temperature? It sure is. So we got B and C both being correct answers. All right, number 7, what is the value of delta G naught at 25 degrees Celsius? For the oxidation of solid elemental sulfur to gaseous sulfur dioxide, given right here. So same kind of process. What is the sulfur S rhombic is 0 plus O2. They didn't even give me, but O2 gas. Why didn't they give it? Because it's an element in the correct state, so it's also 0. Give me SO2 gas, which is negative 300.1. So what is the delta G? Well, products minus reactants. You know, you started at 0, you ended up at negative 300.1. So that is the delta G. All right, I hope you found that helpful. I'll see you in class. Okay, bye.